Okay, so I'm starting by showing you the homework. There will be homework. Who has taken computational? Just you two? You're in computational. Yeah. So maybe we don't do 6, 7. We'll find out. We'll see how bad it is. See if I have it on my other side really quick. So what I like to do at this point in the class, now that we have all these equations, is to go through them at the beginning of class. Let me see if we can pull them up really quick, so that I don't have to write them a million times. Oh no. Oh no. Disorganized Chrismon. Okay.
What week are we? Okay. Not week-wise, but material-wise?
We're still in chapter 4. 4.4. Following along at home, which I hope you are. We are finishing conservation of energy. So we're going to go a little out of order for the slides really quick because I want to start with just discussing the equations, and then we're going to move back to talking about viscous work. So I'm going to put these up on the screen. Can you see those okay? Yes? Okay. So what is this? It's the whole statement.
Well, it's saying, well, it's density over time, so it's the change of density over time, and you're looking at the path it takes from a specific force, and it's saying 0, so it's conserved in that system.
Good for what's conserved?
I was thinking momentum of the energy that's put into the system.
How is that possible? That if there would be energy, how would the energy momentum be equal to 0? Close, almost there. Conserving. Conservation of mass, also called continuity equation. Okay. So I think to Daniel's point, we were talking about there's a rate of change of the density And Trinity said that that is the unsteady or the steady part of the density. And that the only way to change the steadiness of the density is to advect it. So because they both equal 0 added together, we can put the advective side on the other side, the negative. So that says that the rate of change of the density with respect to time must be due to material flowing in or out. Another way to think about that is take your control volume and say, let's increase the density such that this thing is a positive quantity. We recall that this has a direction, right, because of the flow. And so stuff must flow negative inward in order for the density to go up. And similarly, if this thing has stuff leaving, then this goes down. Does that make sense? Okay. So we see over here the steady and advective. So we know what those words mean. Steady is the easier one to understand, but what does advective mean?
It's what that.
Say that the first word again.
It's what's that.
And what is the thing that, what is the cause of the add? Yeah, the flow, right? So the flow itself adds the thing. Right? Cool. Okay, so we can also write this how? Yeah, the one at the top. I can write that in one term. This two terms is secretly one term, which we call the,
Oh, is it the fancy L? It looks like an L, but it's like two loops.
I think you're thinking of classical mechanics. Lagrangian?
No,
It's the delta.
and it looks like. We've used it,
We have?
yeah,
No, we may have used it before, but that's not what I'm hoping for.
gotcha.
Are you talking about reloads?
No.
You mean like rearranging? Or like rewriting?
It's gonna be one symbol.
One symbol.
G.
Well, it's not one symbol, it's one thing. Of row. So I would write something of row. Something is operating on row. In order to give you these two terms. The total derivative. The total derivative is an operator. So if you're taking quantum mechanics, or if you plan to take quantum mechanics, you'll learn about operators. In classical mechanics, sometimes we talk about operators, right? Depending on what type of mechanics you're using. But the total derivative has two terms, right? The total derivative has what? Steady. And the advective. Right? And that's different than a partial derivative of time and a partial derivative of space. But it's the total derivative, adding them together. Good, so when I look down here, what is this?
It's row times and total derivative of one.
Good. So what is this equation?
Gauge partial pressure.
Don't, hold on. Don't read it, because I can read it. That's not what I'm asking. Remember how we started this one before? We said that this was what? A statement about.
Conservation of density.
That's it, right? So I want to start really, really broad. I want to start up here, and I want to narrow down term by term and understand it. So before we jump into understanding term by term, I want you to just look only at this piece here. So what am I saying?
It's the emotional.
Yeah.
That's the meat and potatoes I'm forgetting.
That's the meat and potatoes. Okay, so what if I write it this way? What if I write this as d dt of rho u? What would that mean? There's no advection yet, right? You're right that this has the same form here, but this is a little misleading about the advective term. Because the advective term here uses the ui in order to move the material. But the material that's being moved is only the density. Right? What is this quantity? Rho u. It is the momentum. So this is a statement of which we call. There you go. So this equation by definition must be the conservation of momentum. And it has another name. This is the Navier-Stokes equation. And what do you get if you solve this generally?
Zero. Because it's conserved.
It's not zero though. Look at all those terms. Conservation doesn't mean that the thing equals zero. The only reason that this equals zero is because we can't create mass, but we can create. Okay, so what do you personally receive if you can generally solve this equation? That's right, $1 million. Okay, this is the subject of the, I forget the name of the prize. This is an outstanding problem in mathematics and has been for a long time. There is no general solution for all rho p and t. We have to make assumptions, right? You guys remember me saying that? Okay. So let's start over here. And I want to show you what happens if I take this total derivative of two things that may be changing. I have to do the product rule, right? So let's go ahead and do that. Let's do the first one. Let's do first on rho. I'm going to pull u j out, d rho dt plus rho duj dt. But what is this? Give you a hint, it's on the board. Yeah, which is this term here. What does it mean? What does it equal? You're right that it breaks into these two parts, but what does it equal? Zero. So this term is zero. So instead of writing the total derivative of the momentum like this, we can use the first equation to simply write it like this. You see? So this is still the same statement. We okay with that? Good. So on the left-hand side, we're saying the total derivative of the momentum. And now we have to go through the class and everyone gets to raise their hand and they get to choose which of these terms they're going to describe to me. The first person to raise their hand gets to describe their term and then doesn't have to do it again.
On the second one.
Okay, go ahead. What's the second one? If you get it wrong, you have to do it again.
How density changes when, like with gravity, how density changes with like the amount of stuff above it.
You're close. You are reading density and gravity. That's not what that term means. All the terms are still open. Okay, go ahead. This is like on Jeopardy, right? Okay, go ahead.
Liquid flows with a body force acting on the thing.
That's the word I want, right? These is how we change the momentum due to body forces. And so Kevin maybe gets half a point here for the gravity component. This is how gravity affects the momentum, right? So let's do that. Body forces. All right, who's next?
So the one right after that one, would that be the acceleration of the body? Because it's a second partial derivative over time.
This is over time.
Space, my bad, over a distance. So I'm assuming it's like a acceleration or some sort of speed component. But what's moving?
So since it's over space, can't possibly be considered a speed, right?
Because it's no time. Gotcha, okay. So would it just be the area it's affecting? The area affected by that other stuff?
Yeah, so these terms are your more tricky terms. Okay? The reason you know they're trickier is because you have this one. Yeah, what does this and this mean?
Like the only time I've seen you is in friction.
Friction. So by definition, we called mu what? But we don't use friction in this class. Viscosity is the word. Right? I'm gonna hopefully spell that right. Viscosity. Good. So these last, whether you want to call this one term or two, that's perfectly okay. These last two terms, they are the viscosity. This one?
Yeah.
So where do you see height?
I just see XJ like holding in a direction.
A component in a direction. So that's like 99.7% correct, right? The only thing that I want to grab there is the word height, because you're right in thinking about pressure differences this way, but we can have pressure differences this way. So you're thinking about spatial pressure differences, but we don't have to restrict ourselves only to vertical pressure differences, right? So that's exactly right. So these are pressure forces. Okay. All right, we got two terms left and we got three people. Yeah.
I think that's the income compressibility term, isn't it?
Aha, that's very good. So what do we mean by the incompressibility term?
How what it's able to compress.
Yeah. So thinking about what we're generating here is we're generating momentum. So this claims that I can create momentum from compression and expansion of the fluid. Okay. So this piece here is whose assumption? Remember this one? Oh, from the book. It says that it's generally zero. Stokes assumption. Right, and it's not a law, it's just like, it's mostly zero, you know? Okay, so this term here, generally zero, but not often. And this piece here, in case you didn't like memorize that shape, one thing I want to show you here is this dum dxm. So the way that I read that derivative, see m and m, they're the same unit. So this would be the same as dux dx or duy dy. How much is the velocity changing in the direction it's going? And that, of course, is compression or expansion. So here is your compressibility term. Okay, so that leaves us with one.
If the Stokes assumption is zero, does that mean your compressibility is usually zero in most cases?
The other way around. So generally saying if you have an incompressible fluid, then that last term is zero, right? And that generally comes from the fact that most fluids, now of course you can think of many, many good examples of fluids that are not, right? But when we think about fluids like what we do in a lab, with like a water fluid lab, they're mostly incompressible. And that's why it's a bad assumption. You know what happens when we assume, right? Okay. So what's this middle term that has the viscosity attached to it?
Stresses and strains.
Exactly right. Out of turn, but that's okay. Got to give someone else in the class a turn. Oh, you have a point? Oh, you split your turn? Okay, all right, that's fine. Okay, so these are the stresses and strains. And the way that we see that is from the I and the J. Notice they're not the same. So this is how is the fluid changing in a direction that's normal or tangent to the flow. So how is the X momentum changing with respect to Y or Z, right? So this one here would be our stresses. Okay? How do we feel about this? Kind of helpful to see it all out, right? See it all put together. So we're going to do this at the beginning of every class. Okay? All right.
This is, and on the left is the conservation of mass.
What do you mean? This is the conservation. This is the conservation of momentum, but it's not written very intuitively, because you say, well, how did rho come out? And rho came out because I did the total derivative on both of them. That meant the product rule was necessary. And in the product rule, the first term, the total derivative of the density is by definition here.
Okay.
So we use this here. Right? Okay. Okay, so I'm going to delete everything. Last questions, comments, concerns? Okay. So then what did we do? Yeah.
Made it look worse.
Made it look worse. No.
We rewrote it with all those steps and then we try to get, we rewrote it with the total derivative. Near the end, like this.
Okay. Was it this equation? No, what happened? What is this? What problems do we get when we have Navier-Stokes equation, the conservation of momentum?
We need the assumption.
You need assumption, right? Because let's look at the things we don't know. Okay, this thing. This thing. Right? How are they related? How does rho relate to P? Does it? Usually. But that's the question, right? And so this led us to what?
They do relate though. I think P equals rho KT.
For what? For all gases everywhere? For ideal gas. Does my water behave that way? No, right? And this is the part that's tricky. Right? The ideal gas law you just said, right? That is an example of an equation of state. Very good. There we go. Good. So that is a relationship between P and rho, and they vary dramatically for different fluids. And with the development of an equation of state, we realize that we need another statement. We need operational energy. Right? Is that reasonable? Okay, so then what did we do in class? So we went through and we did the same formalism from before. We took some control volume and we said, how does the internal energy and the kinetic energy change in that jelly bean? And we counted all the ways in which we could either change the kinetic energy or change the internal energy. Or some examples of those. Heating it up, adding heat. So that's Q, right? So I can change the internal energy by adding Q. Anything else?
Doing work.
Doing work. Okay. What kind of works can I do?
Surface forces.
Work by surface forces. And you kind of made the hand motion. What is that called?
Gravity.
Those are called body forces. Right? Because you can't actually pick up fluid, right? But as the fluid moves through a potential, it will gain energy just by falling, which is kind of a weird thing to think about, but we live in a fluid right now. And in fact, when air falls down on us, it heats. That's why if you are at the bottom of like a basin, sometimes it's really warm as the cold air heats as it falls.
I mean, it's moving really quickly though.
Not necessarily. And its motion and its internal energy may not be related, because remember, we had E and 1/2 rho u squared. You can put the energy into either term. You're right, you can get it coming down off the hills and you get the Santa Anas, and they're very, very powerful. Right? But you can also get it to drop down and just be warm. Weird, right?
That's because of like. It's like, because it's actual elevation given in the atmosphere, right? Because I thought like, for example, in a fire, it rises.
Yeah.
So the other, you're saying because of the change in actual elevation, that's why it goes down?
No. So what I'm saying is, just like if I drop something, okay, I take this thing and I drop it. The only thing that happens is it speeds up. Right? and then it hits and it stops, and that energy is dissipated maybe in the form of a little heat at the bottom. But my chart's not gonna melt, right? What I'm saying is if this were a fluid parcel, if I drop it, it may heat up as it falls. Which is extremely counterintuitive, because the only thing you've learned your whole life is that hot air rises.
You guys what I'm saying? I was like.
Yeah. But what I'm trying to teach you today is that the whole fluid is a continuous system. Because in some places, fluid is forced to descend because it's being pushed. Right? We have all of these momentum terms. And none of these momentum terms have anything to do with temperature, or at least not obviously yet. This one here we called what's this thing called?
Pressure differential in space,
Good. So what does that mean?
how the pressure changes.
Yeah, with respect to two different places. So let's imagine, if you will, you have a low pressure area over here and a high pressure area over here, and you have a fluid in between them. What happens to the fluid? Low pressure, high pressure. Yeah, so you push the fluid in that direction towards the low. That seems reasonable. You know how to do that, right? So now, what happens? You can push fluid down from a high pressure system to a low pressure system, despite the fact that this might be cold. And this might be cold. It's fucked up, right?
I think you have more to do with density, like, the colder it is, like, it's more dense, and obviously, like, as things heat up, it becomes less dense, so that's why it rises. Stuff underneath it, there's more stuff underneath it because it's rising.
Yes, absolutely. And so that is 100% the right way to think about it if we're thinking just of hydrostatic equilibrium. So hydrostatic equilibrium says that we are going to balance on one side pressure differences against the gravity field. And if that's how we set up the structure of our atmosphere, then all hot air rises and all cold air sinks. But when we start adding new terms, it becomes much more complicated, right? So what I tend to think about this is like, to first order, right? The first approximation, we treat systems as hot air rises. But because we have many terms, and because we have many things to consider, that may not be the only thing at play, right? Your pressure may not depend only on the density, but also on the temperature. Your density may not depend only on the temperature and the pressure, but also on what's happening to the fluid, right? You can get the density to go up just by putting more fluid there, regardless of changing the temperature. Okay. All right. When fluid goes down, it's called downwelling. When fluid goes up, it's called upwelling. And we see upwelling in the ocean, we see downwelling in the atmosphere. Like a famous example. I'll show you examples of this.
Is that the same logic, but there's like waterfalls operate?
Yeah.
Like if, where there's like steam at the bottom.
Oh, no. That's just aerosolizing the fluid. Yeah. So that's not actual steam, right? You put your hand there, it's cold.
Right.
That would be a huge waterfall in order for it to get hot enough to raise the temperature. When a waterfall falls, right, that is obviously due to body force. And that's pulling it down. But the momentum is mostly in kinetic energy.
Gotcha.
And very little of it is in what you need instead is you need something that is more sensitive to how do I say this properly? Air can do it better for reasons that we'll see. Fluid does it less good. Okay. Yes. Okay, so we had this issue. We attempted to resolve it. We said that we want to think about the internal energy and we want to think about the kinetic energy. And then we wrote more equations. And you're like, man, how many equations are we gonna have?
What?
Who said that? All right. So here we go. Fuck, that's horrible. Dang. Okay. Okay, so that's what's that on the top there?
Internal energy.
Got it. That counts as a term. All right, internal energy. We got kinetic energy.
That, the first parentheses in the middle,
Mm-hmm.
yeah, that's the collision time of.
This is the equation that we did at the end of Monday's class. So this is the conservation of energy. So here I have,
Of internal energy.
this is the internal and kinetic. So we're treating it as one object right now, and we'll break it into two later. The first thing that we do is we think about the jelly bean, we think about all the ways in which the energy in the jelly bean can change. And then once we've added them all up, then we can simplify it. So what's this first term? Body force. You see G, body force. And what is it doing here? What's its job?
Velocity in space.
I think you're like reading it, but what does it do? What are we talking about here?
Oh, how it affects both of the terms of life.
Which are? Right, so this is potential energy. Right? Due to body forces such as gravity or electromagnetism, right? So if I wanted to be a little flippant and I said, okay, we're not going to consider any electromagnetic forces in this class, I could say something which would not be a generally true statement. I could say this is the gravitational potential energy term. Right? And you'd be like, cool. What's this one?
That's heat.
That's the heat. And look, this one looks like the one that we had earlier, which was dp dx. So what does this mean? This is not just heat, this is heat.
Loss or heat.
Yeah, I would call them differences, right? So if, for example, you have a hot thing and a cold thing in contact with one another, that's the same as if we have a high and a low pressure system, right? And in the high and the low pressure system, what happens? Because the
high like goes to low and the low goes to high.
good, so the high goes to the low, right? And similarly speaking here, you have heat where the high heat goes to the low heat. It's the same mathematical formula. It even has the negative sign. It has the same function as pressure, but of course it's a different type of quantity, right? And in fact, when we talked at the very beginning of the semester, we talked that people thought that heat was a fluid that went from one thing to another, that flowed into another object instead of diffusing. And of course, maybe that's not surprising because the pressure differences term and the heat flux term have the same mathematical formula. Identical, right? Okay, then that leaves these fuckers. What are these?
You can see it's like stress tension, right?
That is a stress tensor. This Tij is the stress tensor. Okay, rather than have you work through what these are, okay, I'm gonna pick up kind of where we left off. I'm gonna do a little math board. And then we're gonna end up with these two at the bottom. And we're gonna see how they contribute. So let me see if, I wanna try something here. Oh, look at that, money. Okay, so here's what we're gonna try. Okay. Let me show you where we were. Okay, so I'm gonna write this out. This is rho d dt of E plus 1/2 u j squared. Right? We all get that? What does that first term, the whole thing mean? Conservation of energy. Yeah, I may miss a couple indices here, so if I make a mistake, don't doubt me, please. I'm just a little professor. Okay. This is 4.55 on page 139 of edition 6. I'm just writing what we already had up there. So many letters. Okay. So that's what we had before. I've written nothing new. Okay, and we talked about the fact that we understand this term, we understand this term, we really don't have an intuitive sense for those two middle terms. Okay, so we're gonna do a little bit of a trick. Okay, we're gonna take advantage of some symmetries. Okay, and you can write an equation for the mechanical energy. What's the mechanical energy?
Chemical has to do all with kinetic, but not.
Yeah.
Potential, right?
Yeah, it's kinetic, but not really anything having to do with, say, the internal energy. So let's say I just want to write an equation for, 1/2 u squared. Um, do you remember? Do you remember this guy? What is that? Conservation of what? What? Mass. Mass? Mass? Momentum? Momentum. Remember what we write this as, right? D dt of rho u is equal to,
Just kidding. I tricked you.
is equal to what? We have to do the product rule. Okay, rho d u j dt plus u j d rho dt. So this is,
That's 0.
that's 0. So these are the same statement. So if you see this, it means that. So if you see the left-hand side, it means Conservation of what? Good. And we know what that is, right? We just spent, a good 20 minutes describing it, right? So in fact, I can write it back in one of these earlier forms. I can write it as rho G J plus ddx T ij. Now, why would I want to do this? Well, because I'm sneaky. I'm a sneaker, okay? Check it out. Up here, I want to know what this is. Okay? So I'm going to just be sneaky. I'm going to multiply this thing by rho j, or by uj. I'm going to multiply this thing by uj. And I'm going to see right away that this piece here is present here. Interesting. And this piece here, well, this is Tij, there's some taus in here, so it might be present there as well, right? I might be able to take advantage of the fact that if I use the Navier-Stokes equation, multiply it by U, I get something that's akin to the kinetic energy. And then if I subtract that thing from my energy equation, I can separate the mechanical energy from the internal energy terms. Because some of them are contributing only to the internal energy, and some of them only contribute to the mechanical energy, right? Because over here, we're like, wow, how does this even work? Right? Now we'll know. Okay,
How did you get the right hand side first before you do it?
this one?
Yeah.
This is what we wrote like 4 classes ago, is before we wrote out what Tij was. When writing Tij, we wrote it as the pressure, we wrote it as the stresses and strains, and then we wrote it as viscosities, right? That's how we got all the rest of our terms. It was this plus this one thing, we're like, oh, this is super easy. And then we started to define this, and it was very hard.
That makes up the 2 middle terms.
This one here?
Yeah.
This is not related to this yet. We don't know how they're related yet because we haven't seen this. This is related to the Navier-Stokes equation that we saw previously. Right? The Navier-Stokes equation had pressure differences, body forces, and then a shearing term and a compressibility term. So the compressibility term, that's in there. The shearing term, that's in there. The pressure term, that's in there. And the only term that's not is, of course, the body force. That make sense?
I was thinking how you, I was thinking that what you're doing is you're relating this conservation of momentum equation to the conservation of energy.
Yeah.
And you're multiplying a uj in there, right? So I see uj in the first term.
Yeah.
And you see a uj in all of the middle terms, right?
Yeah,
But there's no uj in the last one.
correct.
So that's not true.
So let's be a little specific here, right? Let's call this equation 1. Let's call this equation 2. Okay, so the first thing we're gonna do here is we're gonna take equation 1, we're gonna subtract u j times equation 2, and that's gonna give us something, right? And then uj times equation 2 is also going to give us something. And it's going to give us 2 different things. Right? Because if this thing represents the mechanical energy, and I subtract it from the total energy, then the terms that I have here should only have to do with the internal energy. And the stuff that I just figured out should only be the mechanical energy. Right? You trust one? Let's find out what this one is. Okay, this thing, if I do it and I multiply it out, I'm gonna write So when, if we put it in there, take the product rule or take the chain rule from the one half, is that right? Good question. Because, there's no halves, right? Where's the constants? Okay, so do we believe this? Does it looks like horseshit, or what do we think? Malarkey? The ex-president used to say.
Possible.
Yeah, what's the first part here? What does this mean? We constructed this thing to mean.
Kinetic energy,
The kinetic energy of the fluid, right? That's good. Good. So the first term. Yeah, it's the potential energy, right? That can. It can affect the kinetic energy. We've seen that. We've dropped fluid. Okay, what's this one?
Pressure.
Pressure forces. Can move fluid. Okay, I haven't said anything new or unusual. And then this one, a little tricky, right?
Surface forces.
Yeah, this is something akin to strains, stresses, something like that. We don't quite know what to call it. We haven't found those words yet. Because we don't really understand yet that this letter with these, we don't have an intuitive sense for what it's doing. But we see something similar, right? So this term here, that's here. So that's certainly not going to be in the internal energy term. Okay. This piece, P du, is that going to be in the internal energy term? No, that's in the middle over here, right? That term is this term,
Oh, you're right, you're right.
right? So U goes on the outside, the dp rho, that's this thing here. Okay, so now I understand what this term is. That is the pressure terms. And that's different than this term. Right? Okay. And we still don't know what this is. So now let's do the top part. Oh, there.
That one. The foremost right one, the second right one on that one.
Yeah. This one?
Mhm.
Yeah. It's helpful that they're grouped, right? Almost like I knew. It's almost like I knew to group them, huh? Yeah. Okay. So in fact, we're gonna write this one here, and this leads to the last equation we wrote on Monday. dTdE is. Someone remember?
Negative P. dV dt.
Negative,
T.
negative P. 1 over rho. We did it.
They have a B. It's the first one over.
What? This?
I'm looking at.
A new?
4.57.
Yeah, a new.
Is it?
A new, not a V. It's a specific density, so it's 1 over rho. So I've just written it this way to make it a little easier. It's not confusing. It's simple. Now, in practice, you could move the row over here, so they have a similar format. You could have the row here, right? And that would get rid of this, and that would get rid of this, and you'd have to rewrite this, right? Because the total derivative of the 1 over rho is a different thing. And we'll do that a little bit. But now can we try to understand what this is?
You again, that is, turn the T to the top.
Which
Which one
one?
got it?
This is an S.
Okay. So just like just tensor and stressor.
Yeah, what's this tensor? There's three different things, right? We have this thing. There's this thing. We have this. You've calculated this thing.
S is,
You did this for your homework.
T is the stress center.
T is the generalized stress tensor.
Oh, is it gonna be like the stream path or something like that?
You tell me. Okay, I'll let you find that in your work. So can we understand what we've written here? Yeah, hopefully, right? Almost. So the top line says the total energy, or sorry, the total derivative of the internal energy is due to what? Good.
Something in the.
Yeah, absolutely. That's the heat flux. Heat flux heats up the internal energy. But one down. This one you actually understand, you just don't know you understand it yet. So what units does 1/ρ have? Volume over mass. So in fact, this looks a lot like PVV. But what does PDV work? Yeah, what does PDV work? I have some gas. Okay. What does PDV work mean?
It's positive, like the sign convention part. I think negative is when you press it.
Yeah, sure. Well, compression is what I'm asking. PDV work means compression and rarefication. Right? So here, how the density, 1/, the density changes, which is the volume, how the volume changes the internal energy. Compression and rarefaction heat or cool the gas. Right? So we actually do understand this term. It's PDV. Okay. All right, and then it's just this thing we don't understand, and this thing we don't understand. Okay? They both have these. Both have stress tensors. So we can be very hand wavy about it. And we can say, well, they must have something to do with the viscosity of the fluid. Right? Do you know which is which? They have specific names.
Both directly like deal with Wisconsin.
Yeah, they do.
So you're saying like S is strain and T is stress.
What?
That's what you're asking. Like which
No,
is.
no, no. So we have one here that talks about the mechanical energy or the kinetic energy, and one here that talks about the internal energy. And we have two terms related to the stresses in the fluid itself. And the stresses are only communicated through viscosity and the intermolecular collisions, right? So in one case, those stresses generate internal energy or take away internal energy. That means they're creating temperature or they're decreasing temperature, right? And in another case, they are generating kinetic energy or they're taking away kinetic energy, right? Okay.
Is there an example of it raising internal energy?
Hands hot. Why are your hands hot?
Okay, I thought that was mechanical. So is there an example of the other way of it being mechanical?
Yes, that's harder. It's much harder. Okay. So how do you generate kinetic energy from stresses and strains?
Make it as incompressible that it causes it to move.
Yeah, this is our surface forces acting to create momentum. Right? But momentum and energy, of course, are related, because the velocity goes up, the energy goes up. So it's the same generation. Right? This piece here is the generation of kinetic energy by surface forces, by frictional or viscous forces. So this is the viscous work term, right? And then this is the viscous heating term. And this is, we just, sort of throw these words together because we can understand how these different terms exist. But when we start to use them in practice, they'll make more sense. Okay. That took a really long. I'm not gonna redo all that because I want to go back to this other slide really quick. Oh shit. Oh my God. Disaster. Okay, wait, there it is. Where'd it go? Okay. So look, I even wrote it down. All right, here's what I said. We can define the viscous work as the kinetic energy dissipated into the fluid. These play an important role in turbulent flow. So we were talking a little bit about the idea of eddies. These like things, they curl around and they take the kinetic flow and they turn it into. You can also have high shear locations. What would be an example of a high shear location in a fluid?
And then,
So I think you're thinking about geometric shear, and that's certainly correct, right? So shear would be like if it's changing its direction. But I'm thinking about shear here as being two different flows moving past each other quickly. You experience high shear every day, probably.
Like a car in the air.
Driving a car in the air. What do I mean by that? Let's think about the car really carefully. As you drive in your car, right, you have a little bubble of air moving through. You have this big hunk of metal all around you. And you're doing 80 miles an hour on speed on the freeway because you're a little late to class. Okay? You roll your window down. What happens? Everything in your car gets fucking sucked out, right? Oh, the little burger you're eating, all the paper flies out, right? Okay. That's certainly a high shear because you're having a fluid that's basically at rest come into contact with a 80-mile-an-hour. And then what happens is you generate eddies. You generate small rippling currents that then pull dramatically the material, the fluid inside your car out and try to accelerate it. That is taking kinetic energy, dropping it into your car, right? Another way, and we'll see this shortly, what is the air velocity on the molecules that are touching your car? Probably never thought about this.
Is it zero because we're not considering the volume?
0. The molecules that touch your car are at rest with respect to your car. Okay? And then they move off to whatever speed elsewhere. Because it's a fluid, it's continuous. So the boundary where one fluid touches something that's not moving or whatever, okay, if you have the fluid at the bottom, touches the fluid, touches some object, it has to match that velocity. And we'll find that there, for example, on the front of a car as it moves through, you could have air over here, it's not moving very fast. Your car's plowing through, being dragged along at 80 miles an hour. That air creates a little boundary around your car, very fast air, running into very slow air, and that is high shear. And the way that those interact, right? Sometimes you see a plane with a little cone. That would be like a shock wave. So that would be the highest shear that you could think. That's really when a fluid is not able to even communicate to the rest of the fluid that it's being broken. It's moving faster than the propagation speed. Okay. Okay, so we can add in heat transfer, and we can think about the ways that heat transfers. So you can do like thermal conduction. I guess basically you would just take, well, let me just do it. Do you know Fourier's law of heat conduction? Never heard of it. Okay. What?
I just carried my bag.
Okay, so this piece here we can rewrite, and we can write this in terms, so we can rewrite these terms in the same format that we had previously with like S and pressures. But this thing here can basically be written so for fluids, this is mostly true. You mostly have diffusion of heat. But this certainly would not be true. You know, if you're thinking about all of the ways in which to generate internal temperature, you could imagine there is a really good way of heating up fluid. And that is very common. Say, let's say it's summer. How do you heat fluid? Say like a big body of fluid that you want to go jump in. How do you raise the temperature? What do you do? Let it sit outside. Yeah, the sun's really good at raising the temperature. So that's not what I'm writing here. This is dQDI, right? That would be the addition of heat at the surface. So the mechanism by which we do it at the surface can vary dramatically. You could have a term here that's just like add heat at the top due to light, right? And then it like percolates in. But when you use Fourier's law, it's written like this. Okay. So this thing here is Q. And this piece here. Okay. Fourier's law is very common in the diffusion of temperature. If you have a high temperature region, it'll diffuse, and that generates heat. Heat, of course, is a different quantity, mathematical energy unit. Heat, as opposed to temperature, is not an energy, right? Even though they use interchangeably words. Okay, and so this, generally speaking, satisfies the second law of thermodynamics. Right? Changes in the internal energy are due to PdV work. They're due to TDS work. This is the TDS work. Temperature, changes in entropy, and stresses, viscous stresses. They're in the fluid itself. That makes sense? It's okay if you don't feel like you're an expert in this yet. You're gonna do 3 things this weekend. Okay? You're gonna reread the section that we had on the temperature. First and second laws of thermodynamics as we wrote them in the first couple weeks of class. In the very first chapter, we went over it, let's refresh it. And then when you see PDD, you're like, oh, fuck, that's what PDD means, right? That's what TDS means, right? Okay, so those are the things you want to think about. You're gonna reread those 2 or 3 equations. You're gonna read the continuity equation, you're gonna memorize, okay, what does this term mean? Not memorize, but understand. You'll read the continuity equation, and you'll read this energy, conservation of energy equation. Okay? And then once we're done with that, we're done. Okay? That's all we'll have to say about any fluid ever again. Everything else is a special form. So we will learn how to use these 3 equations together to solve fluid dynamics for specific examples. So whether that means solving planetary scale waves, whether that means understanding how water in a cup rotates, you can do that with just what we have built. Okay? And generally speaking, we will see some examples of very simple fluids, but almost all fluids needs to be done with a computer. So you'll see some, for example, simplifications that we can solve on the board. But almost everything that you'll do in your real life will be. Okay, so if you haven't used a computer before, computational, maybe don't attempt homework 6, but if you have and you want to try it, it'll be fun. Questions, comments, concerns? Okay, we will also do this at the beginning of every lecture. I'll be ready.
Professor.
Yeah.
Are we gonna be able to cover chapter 8 during this semester?
What's chapter 8?
Gravitational waves?
You understand that that is not like for stars.
No, but I mean for planets, or is it not astronomical?
It's not astronomical at all.
Can it be applied?
You know.
Okay, cool. But everything else can be applied to it, right? That we've learned so far, like how you mentioned this can be applied to other stuff.
Oh, yeah.
Okay.
But, so chapter 8 is gravity waves. We will do those, but we will do those in the context of what they were meant. So when gravity waves are first talked about, they are the result of waves that are due to the fact that there is a balance between the fluid and the restoring force gravity. So things that are buoyant versus things that are sucked down.
So the way they first calculated gravity was just by like that time it took for it to like stabilize?
No. This is fluid dynamics.
Got it.
Comes way after gravity.
Okay.
Gravity comes from 2 spheres that Cavendish watched for a really long time. We could do a history of, I think we should do a history of physics class someday, but not here. Okay,
You have times available today? Or no?
for homework or for?
Or-
Oh, right.